Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. It's been a few weeks. Sorry about that. I meant for it to be 3 weeks and ended up being 4. Um, well, actually, it ended up being 5, didn't it? Because I took... No, it ended up being 4. I knew I was taking 3 weeks off. Or was it supposed to be 2? And became... You know what? Screw it. I don't remember. I took 3 weeks vacation. And one of those weeks I was supposed to stream and didn't. Because we ended up staying at the in-laws a week longer. Which was good. And I did a lot of work during those weeks. Had a lot of the time with the family and a lot of the time with my computer. And I like that balance. So I didn't really prepare in catching you guys up. So I'm just going to run something and we're going to talk maybe backwards from there and just see where we're at. And then talk about what I'm working on now because I've decided to change direction on parts of it. Which I will try to motivate, and I think you guys will agree. Let's see. So we'll start just by running this. And what is this? This is... Oh, hey, wait a minute. I still have window capture for this. Let's get rid of that. There we go. All right, so what this is this is a test window. I think this is testing... Let's see what resolution this is actually running at. This will be in MISC struggle, which I'll talk about what that is. Main. Yeah, 16 by 8. Which... Yeah, 128 by 128 pixels. That's what we're looking at right now. Let me update my size here too. Yes, just 128 by 128, and that's to make this a little faster. The geometry itself that we're seeing here is just a bunch of random cubes with a particular texture. I can show the texture there too. And then I'll talk about what we're looking at in more detail. Dev. Come on. I think it's this one. Well, that's a big window for a small texture. I believe this is a 16 by 16 texture, and this is literally just something I drew in Paint with a bar and this stuff. And the reason I drew this is because I was testing additive blending, which isn't actually applied to all the triangles here, I think, but you can still see that it happens on some of them. And there's a few reasons I kind of built this. I'm also going to show a faster version of this and explain the difference. So this is a bit faster, and you can see a little more clearly what's going on. So basically, what I had before, which I kind of bootstrapped on stream, was a way to drive the GPU where we actually talk via a simulated UART to the CPU and then sort of forward commands and data transfer with that mechanism. And that ended up, like, while it gives me a lot of peace of mind that like the whole system works, and I can also take that exact setup and just turn on the FPGA and just switch it over, like it's the same code on my host PC, and whether or not it talks to the simulated device or the actual device on the FPGA is a small matter of programming. Anyway, that setup is really nice, but it's also really slow, and especially for testing a lot of these features. Like I was debugging a bunch of blending stuff and filtering, texture filtering. And that really sucks to have something that moves that slowly. So what I ended up doing is I bootstrapped a simulator harness just for the GPU, which I actually think I started with a while ago. And I went back to that. And I also have this set up so that it runs in either a simulator of the actual RTL or what we're seeing here, which is obviously a lot faster. And this is a model implementation. This is basically, I took the GL, the thing that I made behind the GL back in like November, and I moved it over towards where the RTL is. It's not exactly feature parity, or actually feature parity it does have feature parity. So like they do the same stuff, but this one, the texture filtering is actually broken, I think. So I think this basically has a quarter res version of the same texture. And that was because I was being lazy. And that turns out to kind of work in my favor because I think I'm going to change how the texture cache works anyway. So I'm glad I didn't spend time implementing it twice. But anyway, it's kind of cool seeing this. In fact, I'll bump up the resolution, which I think will be fine for the model here. It's probably going to be really large with the zoom. It is, but that's kind of cool. So this is 320 by 240 and then scaled a bit. You can see this is quite smooth. Again, the texture filtering here is a little broken, but you basically get a filtered version of a low res texture. So again, just some test geometry, but that was also kind of to see where where I was at in terms of performance estimates, because I still haven't done a proper pipeline in the system for doing geometry transformations. So I still need to do that, but I wanted to see where the rasterizer was. And I came to some conclusions that I'm not terribly happy with. So this is running at 320 by 240. And the other thing this does is it prints out estimates for some of these things. So every time it does a frame, it estimates how many cycles it took to draw that frame. And it categorizes different cycle counts here. So we have this regs one. This is the amount of cycles spent approximately just writing registers to the rasterizer. This xver number is how much time we spend moving data in and out of the rasterizer. So either if we're moving in color data or depth data or moving those out, or if we're moving in the texture cache, which is explicitly populated in this architecture currently, all that gets added here. And that's just an estimate, but I think that's a pretty good estimate. Whereas this regs one, I think, is a bit on the low end because my CPU kind of sucks right now. And then, oh no, actually it looks like, no, this is something else. Yeah, so that last one is this bin read and write. So as a lot of you guys know, I'm doing a tiled renderer. So this is broken down into 16 by 16 tiles or whatever other size. I've implemented it as 16 by 16, but I can actually change that. And this does seem to be a sweet spot with some of the test geometry I have, but I might change that later. Anyway, with a tiled renderer, you add this extra stage. So if it's not tiled, like in a medium mode renderer, you take your vertices and you do the transformation, and then you assemble primitives after that, and you might do culling and stuff, and then you just pass those triangles directly to the rasterizer one by one, and the rasterizer will go and draw the whole thing. And that is a simpler architecture, but it should be a little bit worse in terms of performance. Typically for I guess if the common case is just flat shaded triangles with no texture, that's kind of a good way to do it, because you can construct a rasterizer that's only going to touch the pixels it needs to, and there's just going to be a bunch of writes. But as soon as you additionally support textures and depth testing and blending, you end up requiring a lot of memory bandwidth, and this system doesn't have that much memory bandwidth. I think I calculated it's like 1.2 gigs a second, and that's actually gigabytes a second. That's actually double what the N64 had, it seems, which is kind of interesting, but it's still not very much. So I chose to do a tiled renderer, and that way I can, with a tiled renderer, you add another pass between the transformation and the rasterization, where you do what we call binning, and that's where you take all the triangles that you're going to draw, and you actually maintain a list for each tile, and you say, okay, this tile intersects, or I mean, this triangle intersects this tile and this tile and this tile, and so you add that triangle somehow to a list in memory that represents the list for each tile. So each tile has a list of triangles that's going to draw. And then what you do when you rasterize is you pull like the pixel data and the depth data into that buffer, and then you draw the triangles, ideally at a faster rate than you would have to main memory anyway. But that may not be the case, as we'll see. And then eventually, once you're done with the tile, you ship all that memory back out. And that's a pretty good design. However, the way that I architected mine, I think there are some fatal flaws where that's not a good design choice. And I kind of figured that out while I was working on this stuff, because you can see, if you look at some of these cycle counts, I know this is a small font size. Also really quick, you can see that the estimated frame cycles is whatever divided by this number, or out of this number. This other number is at 100 megahertz. This is about how many cycles we have per 60 FPS frame. And so then I give a percentage about like, here's how much frame time I'm spending just doing all the stuff for rasterization, which you can see is quite high. And in fact, in this model, you can see rasterization is 0 because I don't estimate that in the model. In the sim, we can see it's even worse. So again, this is the actual simulated RTL for the rasterizer. It runs a bit slower, which is why I have both. And you can see here, there are frames where we actually blow the 60 FPS budget. And this is like on the order of hundreds of triangles. This is not good. And this is just rasterization. Again, this does not include geometry transformation. But the other thing you can see on this is about half of that time is spent in rasterization, which is fine. I mean, we do want half the time we're using, or like we want half or more of the time that we're using to be on rasterization, but it's actually less than half. And then the registers and the transferring moving data in and out of the rasterizer and everything, that's not very high. But this binning cost is actually enormously high. And first of all, this is a very conservative estimate. I'm doing a really dumb version of binning right now, where I take the transform triangles and all their parameters and I add all of those to lists. And I'm not doing that on the system, by the way. I'm just doing this in my like setup code, and I've just estimated how many cycles that takes. Which, first of all, I think this is a conservative estimate because, again, my CPU sucks. Which we'll get to. And then second, yeah, it's a really dumb scheme, so I need to come up with a better way to represent those bins and do the binning as well. So we'll tackle both of those, or at least I'll share my thoughts about what I'm thinking for those. But anyway, this is enormous. This is really high. So this kind of freaked me out when I first did this because, again, even though it's conservative, it's still really significant. And I had kind of been ignoring how expensive that pass would be. Because essentially, like if you're drawing a normal pixel of one of these triangles in like any renderer, you need to read the depth that's already there. And you need to potentially write the depth. You need to read the color that's already there if it's blended, and potentially write that color as well. And you need to read texture data. And that's 5 different like memory operations that you need to do every pixel. And with having all of this in like local caches in the tile, that can all be done extremely efficiently. So like we actually output a pixel per cycle in the current rasterizer. I want to scale that up, and I'll talk about that too. But that's pretty good. But if you were going to do that to main memory, you'd have to end up either like serializing all those or sticking a cache on the side of it, and then you have to kind of schedule all that. And I think what would end up happening is, first of all, you'd spend a lot of overhead reading and writing the same pixels to and from main memory, especially if you're doing a lot of blending like you do here. And in that case, the tiled approach is going to be a lot better because you're just doing everything in like the local tile cache. And by the way, I want to support blending. That's a pretty important feature I've decided for the kind of content that I actually want to make with this. So that needs to be supported, well. And depth testing is another thing that I want to be supported naturally. So anyway, with a tiled renderer, you kind of batch up all those requests, which is really nice. Except textures actually present kind of an interesting problem too, because if you have like a triangle that covers like the whole screen, if you're going to rasterize like the whole triangle, like scanline by scanline, depending on the size of your texture cache, you might actually be missing that cache a lot. Like if you go across the screen and you end up like evicting some parts of the texture over here as you're pulling parts of the texture over here, then by the time you go back, that might be out of cache again. One of the things, there's a few things you can do about that, especially with these like Pineda style renders. You can like go back and forth, and that can kind of help. But the tiled approach also tends to work well with the locality of the textures, of the texture memory. In addition to that, eventually I want to support MIP mapping as well, which should also help with the texture cache. But yeah, I don't know if I mentioned this, but right now the architecture actually, for every draw call, it creates a new bin, like list of bins, and pulls all the data in and out of memory, like for every draw call. And I actually want to overlap draw calls, so that each tile bin actually contains triangles from multiple draw calls put together. That's kind of the ideal case, because then you only ship color memory in and out of the tile like once per frame. However, one of the things that's blocking me from doing that is the fact that I have this explicit texture cache, which actually loads the entire texture into a local cache in the GPU. And first of all, that texture cache ends up being potentially quite large, so that's kind of dumb. And second of all, that means I'm not actually able to have triangles that cover multiple draw calls in the bins, because I either need to, in the middle of drawing all the triangles for a bin, I need to ship a new texture in, which means I'm shipping in that texture multiple times, or I need to do what I'm currently doing in this test setup, which is where I do, per draw call, do all the binning and then rasterizing. And that means I'm shipping the color and depth memory in and out of the tiles more than I have to. So a better approach with or without this tiled renderer is to have a texture cache that acts more like a normal kind of CPU cache. And this is what modern GPUs do as well, where you do mip mapping first of all, because then you can determine which levels of textures that you might actually read. And it turns out you can probably save a lot of bandwidth just by not reading that much texture data in the first place. So that's going to be helpful. And second of all, that way the tiler will, pull all the color and depth memory into the tile, and then as it's rasterizing, it will determine the kind of texels that are actually needed and then go and fetch those from main memory as it's rasterizing. So that does complicate things a bit, because that means we need to add another data path so that the rasterizer can actually go and fetch that data if it has to. And also, we may need to stall the pixel pipeline. So it's going to make things a bit more complicated, but I think ultimately it's going to be more performant. And that way we can also make that texture cache a bit smaller, because it doesn't always have to hold the entire texture. And then more importantly, we save a lot of bandwidth overall by not moving more texture memory than we have to, and not moving the color and depth data in and out of the tiles more than we have to, ideally. So I think that's going to be really good. And I think I used to be more afraid of implementing caches than I am now, because I just didn't really trust my ability to design RTL. But I'm getting better at that. And I think especially now that I've written a lot of this infrastructure, like one of the components that I have in here is this like reusable bus component that can do memory mapping and some other things. And I think I can just rely on that to like hook up a lot of this stuff. So I feel like I'm getting more comfortable with that. And I'm more comfortable with the idea of giving these individual hardware units DMA access instead of having all the DMA run by the CPU. So I think the texture cache is going to be a really good like pilot for doing that on these units. Yeah, exactly, Daniel Collin. I think that's definitely the way to go. And otherwise, I'm just wasting a lot of like bandwidth and stuff, which, yeah. And I think, again, I still need to optimize the spinning pass. And that kind of leads me to the next thing. Or actually, before I move on, there was another detail and another reason I want to do the texture cache that way. Or maybe not the texture cache in particular, but another change that I need to make is that if you want to do mip mapping, you need to render at least 4 pixels at a time. You usually do that in a 2x2 grid. So within the tile, you would render, instead of 1 pixel at a time through a pipeline, you would have 4 parallel pipes, and then you pass little blocks of 2x2 tiles into those pipes. So first of all, that should accelerate things because it'll have more pixel pipes. And then the other stuff is, sorry, I lost my train of thought right in the middle of talking. But yeah, it's faster. And then the other way is that then you have that 2x2 block. And when you get the texture coordinates for all those 4 pixels, you can then subtract, the left and the right one, and then the like top left and bottom one or whatever. And you can determine the partial derivatives for the texture coordinates for your actual block. And that's how you actually determine the MIP level for the textures. So you actually need to be producing 4 pixels at a time. And this actually also, so this was related to texture cache when I think about it. This is kind of a problem because right now I have the texture cache set up so you can it only supports reading 1 pixel, one filtered texel per cycle. There it is. And there's a couple ways I can help with that. I think I can actually make it 2 without really any change because I think all the memories that I'm using for this are dual ported. So I think I can just use the other port on these memories. But then I also, if I'm going to use that mechanism then to get 4 per cycle to feed 4 pixel pipes, then I need to also double the memories. I'll have to use some duplication there, which in terms of bandwidth is fine because I'll just write to both memories when I read that data in. But in terms of capacity is potentially problematic. And right now, the max texture size of 128 by 128, which was decided because I know I was shipping textures all the time, that was going to be like 64K worth of memory just for that texture cache. So I'm thinking I can make it, a lot smaller practically, and support larger texture sizes by doing just like a regular cache. And that way I should be able to feed more pixel pipes, which will fit well with also having MIP mapping, which will ultimately save bandwidth. Right. So it's like all these little related things that are all supported by just changing how the texture cache works. So I'm definitely going to make that decision. Yeah, Daniel Collin, totally. You mentioned you can swizzle textures as well to improve cache cycle. That's actually what I'm doing now. And that's why I said I can read one filtered texture per cycle, because the memory now is actually in 4 different banks in little 2x2 pixel blocks. So I'm already doing that. But then I need to, or well, that's actually to read 4 at a time. There is another level of that, which you also might be talking about, where you can do like Morton ordering or something else with the actual data, like on the next level up. So yes, I'm putting the 4 in different banks, but then in addition to that, you can also like support a better local order. So that's maybe that's what you meant. Yeah, totally. So yes, I want to do both. Right now I'm only doing, I only bank the memory. But yeah, what you're talking about is swizzling the textures, which will also improve cache locality, which is definitely something I want to do. But I haven't done here because here it doesn't matter yet because it's all in local memory. So, but again, when I change this to a real cache, that will definitely help. So it's a lot of talking for, I think, what is a fairly minor change. But I think that's where I'm going next. But I'm not there yet. I need to start implementing these kind of caches and think more about how that's going to feed the pixel pipes. So I'm glad I got to show the current state of things first, because I don't think there's going to be very visual improvements to the system for a little while as I kind of work through how that's going to work. Because it's easy to say I'm just going to do this cache, but it turns out those are kind of hard to implement, at least if you haven't done it before like me. So been going through that. The other thing is that as soon as I open the door to caches, then that makes me think of, okay, or first of all, one thing, I'm opening the door to caches in the system at all, which I was kind of hoping to avoid in general, just because it adds complication. Yeah, exactly. Like I totally want to bump the texture res too. The 120 by 120 was purely driven by that texture cache size, which then wouldn't be a problem because then like a 16K texture doesn't need to hold the whole texture anymore. So anyway, you totally get it. So the other thing is this bidding time takes a long time. And again, I'm not using a very nice scheme for this. But again, when you're thinking of caches, like that should be something that I can also apply to the CPU. Because right now I have this really dumb CPU design where, let me look up some diagrams here. Risc pipeline. I only need like a basic diagram here. This is from, give me some from like Wikipedia that I don't mind putting on stream. Okay, this will work. This is the classic risc pipeline article on Wikipedia. And okay, so for those of you guys unfamiliar with this, this is the idea that like in a classic risc pipeline, which I sort of have right now with the CPU in my system, I think I have 6 stages right now, which I think I can reduce to 5. I might work on that. Anyway, each instruction in this kind of architecture takes 5 cycles. It might take more if like one of these memory stages needs to stall or something, but generally this is the case. I'm also ignoring bubbles for now, but the idea is that each instruction takes 5 cycles, but you can overlap the execution of subsequent instructions as long as there's no like hazards between them, such that you can actually process or retire one instruction every cycle, even though instructions took 5 cycles. So you get like a 5x speed up versus the dumb version of this. And right now, the way I'm actually implementing this is I have each of these different stages as different hardware units. But to simplify things, I just have a little state machine that just runs an instruction here, and then this stage, then this stage, then this stage, then this stage, and then it will go and get the next instruction. So I'm basically executing it the dumb way, even though I have a lot of hardware available for the fast way. So I need to change that. And that's definitely not a trivial change. I think that'll take a lot of work, but I think it's just something I have to do in order to improve basically all of the time spent per frame, and especially the time spent binning triangles, which I suspect is going to be kind of difficult. I'm still planning on doing that on CPU. Maybe eventually I'll move that into hardware, but I'll do a CPU implementation of it first. Anyway, in order to do that, there's actually another crucial thing that you have to do. Because when you overlap these, you'll notice instruction fetch and memory, like for load and store, can now overlap. And currently, I just mux these two things. So there's actually one bus to and from the CPU, but actually the core of the CPU needs two buses. It needs one to supply the instruction fetch and one to supply like potential load or store within the same cycle. And the only way you can do that if it's connected to a single memory is either dual port that memory, which is not going to happen because it's ultimately DDR memory, so I don't have that option. And two is to put caches there. So the simplest kind of version of this, which I've seen a couple places in particular, I think the Virtual Boy CPU does this, if I remember correctly, is they only do an instruction cache. And the nice part about that is an instruction cache is only one way. You only ever read from it. So sometimes you might have to invalidate it, but anyway, as long as that can satisfy a read or write per cycle, then we can actually overlap these stages. Eventually, I do want to put a data cache on here too, but I'm going to start with this kind of read-only instruction fetch cache, which incidentally ends up being simple, or not simple, similar in at least functionality to the texture caches, which are also kind of read-only, but sometimes you invalidate them. However, the data organization and other like implementation of these details of these might actually differ, but I'm going to probably try to get away with just having like the same thing, the same unit maybe, or maybe not, I'm not sure. But either way, to kind of satisfy both of those needs, I've started actually looking at a read-only cache implementation just to start my foray into making caches, because that's something I have to do here. So that's kind of some things that are changing. Is I'm going to put caches around the CPU, and then I'm going to actually try to do proper pipelining on it. In addition, I'll do that texture cache properly, which will be really nice, and then give the GPU the ability to do DMA when it needs to. And I think both of these will definitely help performance, which I haven't actually measured because I still don't have the whole pipeline, but I've estimated. So these estimates I think were really useful, doing these early and doing them often. So yeah, I'm happy with this progress. Again, the features that I implemented are blending. I also implemented depth testing. I implemented texture filtering. So I did quite a lot of work, and I'm pretty happy with this, how this is going. But yeah, we need to make some proper changes. And that's why the title of this episode is Caches. It's because we're probably going to start working on that. So really, really pleased with my work the last few weeks. I haven't been able to work on it too much in the last week or more because of other things that have come up, but that's fine. Oh yeah, and the other thing that's kind of part of that I mostly made to simplify testing is I made this other project called Struggle, and this is just a project within the XenoWing project. And here I'm kind of starting to define what like an actual graphics API that you might use from the XenoWing might look like. And right now it's really similar to GL, with some abstractions just not there yet, but it's still cool to see. So right now, the way I'm doing this is I create this context, and I actually do this every frame, which I don't need to do eventually, but whatever. And then here I only have one texture in the test, so I just upload that, but eventually this is going to be part of like texture objects as you would normally see in an API. And also this upload won't happen, as we discussed, because that will all be handled by the texture cache. Although sometimes that will need to be invalidated, and we're going to figure out when that needs to happen and why. And then on this context, I'm just setting this depth test enable and depth write mask enable thing. These, I imagine, will be replaced by API calls. But right now, I'm just setting them on this object because all this prototype stuff is in Rust. Then I figure out this projection matrix. And you can see, again, this very like GL 1.1. Kind of on purpose. I don't know if I love this API, but this stuff works. So I make a projection matrix. I do some stuff with time for view matrix. I had something else that I was rendering because I can also, I forgot to talk about this. I can change the texture filter. So right now it's bilinear, but I can also do nearest, which I don't know if it will make much of a difference on this test scene here. But that does work. Yeah, it does actually make a difference. That's kind of cool. So that's the other thing is in implementing these, it's like doing all these little options is kind of annoying, but it's also kind of fun to see how they're implemented. I can show that in a minute. And then, yeah, set these blend settings. Again, looks like GL, and then eventually render it. So the c.render, I think, is basically issue a draw call. So it's this kind of immediate mode API, which I don't think I will have eventually. Eventually I'll have like proper vertex buffers and send those. So I think that'll be a lot faster. And especially better for static geometry, whereas right now I'm drawing like 50 cubes, which again is not that much. And you can see that those cycle counts are pretty bad. So the resolution I'm targeting is 320 by 240. I wanted to target 640 by 480, but when I started looking at all the features I wanted and the clock rate that I want, it looked like I could do cooler looking stuff with 320 by 240 at 60 FPS than I could with 640 by 480. But I might actually make that configurable because it's not actually that much different for most of the pipeline. And the video output itself will be 640 by 480 because that's going to be the actual resolution that the hardware outputs, and then it'll just use scan doubling when it's less than that. And I think a lot of consoles of this era actually made that configurable too. So maybe I'll do that. And then you just take a performance hit in the cases where you're using 640 by 480. But the cool thing is it'll never interrupt the actual video signal. It'll just change whether or not scan doubling is done and how those caches work. And of course, the amount of data that you need to pull out of cache. I think that was actually another thing that at one point I did some estimates for how much frame time it would take to actually pull the pixel data out just for display. And it was like 15% or something, or 30% with 640 by 480. But I think that's actually not true anymore. I think that was before I was batching the reads and writes properly to the DDR when I made that estimate. I think it's like 0.1% or something now, so it's definitely affordable, or maybe 1 or 2%. I don't remember what the value is, but yeah. So yeah, I think that'd be cool. Yeah. Anyway, the rest of the stuff is just, again, like I keep duplicating this code for like triangle setup, but I'm just gonna keep doing that until I kind of get everything I need in there, and then I'll massage it better. Because there's also, like, the way these are written, all this triangle setup stuff, these are the kind of wrong ways to do this, but they're the simplest ways. And eventually I might try to make this fixed point or something. Again, I still don't really know how I'm going to do vertex transformation and everything yet. And triangle setup, I don't really know. And that's one of the reasons I'm planning on using the CPU to do it, because until I figure that out, I don't really know a good way to accelerate it. So we'll figure that out first. Hey, Finrog, I have no idea what pilk is. But yeah, anyway, cool stuff. Oh, Pepsi milk. Is that like a Pepsi, what was it, milk Coke? That's so gross. Anyway, I wanted to share some of the RTL here because this is kind of cool. Oh, first of all, I want to do something here, because if I go to make generated RTL, just like doing this. Am I dropping frames yet? Probably not. I don't think I drop frames when I'm only compiling one project. So anyway, there we go. This is the Xenowing right now in actual Verilog. And this is getting larger and larger. This is now 10,000 lines of Verilog code generated. I mean, to be fair, the Rust code is also getting longer. But yeah, it's always kind of fun. No, I didn't fix the OBS priority. I'm too lazy about it. But yeah, I wanted to discuss some of the bugs I found, because this was actually fun. I'll pull up some screenshots and then kind of show you guys how I messed up. Because I think that's really cool. Let's see. I gotta pull up my Twitter because that's where I posted all this stuff. Here we go. Did I change it? I don't remember that. I must have done that on the stream a few weeks ago. Yes, some earlier shots. And then here is when I started getting texturing working. 2nd of July. Yeah, and here there's actually something interesting, because I here's where I first got texture working, and also multiplies with the color of the vertices, which is kind of cool. Oh, you did it, Chief Detector? Gross. That's funny. But yeah, so here, like I had texturing working without filtering, but there's kind of a crucial thing. This actually should have been perspective correct, but then I was fixing the 1/W to be 1, which just made it easier to test before I hooked up like a 3D, like proper transformation stuff in front of it. And I thought it was correct, and it actually totally wasn't. So here I did filtering, and this is where I did that, put the different pixels in different banks stuff. So that took a little while. I describe it on Twitter. There's also this seam bug, which I'll talk about in a minute because we'll get to there. But I was kind of ignoring it because that was something else. Whoops. But then here, this is the fun one. So this bug, again, ignore the seam, which you'll see here. Still, that's the same bug as the seam in the other one. But I didn't know it yet until I saw it with perspective. This bug was kind of funny. So what had happened is I have this approximate reciprocal pipe. And so the first thing that you do, that the pixel pipe does, is it's going to calculate 1/W, and then it's going to multiply the 1/S, 1/T texture coordinates by that to do this perspective correction stuff. This is really standard. Like this is the way that you do this, because those interpolating those in screen space is linear in projective coordinates, but it's not in, or at least that inverse is linear, but not the actual values. I really still don't understand projective geometry very well, so I can't really explain it better than that. You just have to know that it works. But this got really crazy. And what had happened is in my approximate reciprocal pipe, I had to add some like additional register bits, or not register bits, registers in the pipeline. What's all that? I have no idea how all this suddenly got underlined, but whatever. Oh, is that mutable ones? Oh, that's kind of a nice feature. I like that. Or maybe not. I don't know. Whatever. Anyway, I had to add some additional register stages to this pipeline in order to meet timing on my particular device, which is fine. But I didn't actually properly pipeline all these values. Like this one wasn't properly pipelined, and I think the shift wasn't properly pipelined. And what that meant is that some of these parts were actually using stale values from like earlier in the pipe that weren't propagated properly. So it worked fine if I did one multiply at a time through the pipe. But then when I actually did the real thing, which is piping, 1 pixel at a time through the thing, then it got crazy values. Luckily, it wasn't that hard to track down, right? Because this doesn't have that many different parts in it. And I also noticed when looking at this, first of all, it was probably something with the perspective correction, right? That's obvious. And again, it was correct when I set W to 1, so I figured it was part of that. But also looking at this, you can see there's clearly block artifacts here. And I remember changing the tile size like to verify that, and it does follow that. But also, they're only horizontal, not vertical. Like you don't see boundaries on the blocks this way. And so I thought it must be something with like the interpolation, not the triangle setup. And then what else is there if you just do like the texture coordinates? And so it must be that or the reciprocal. And it turns out it was, when I looked at the code, it was pretty obvious that in particular this value wasn't propagated. And then I looked at it a bit more and realized the other one wasn't. Luckily, in this setup, I'm doing a lot of simulation-based like unit tests, especially for stuff like this, because I want to make sure that it's correct. So this is the approximate reciprocal code, and then I have the sim test for it here. That just here it just generates one of those, and then in the test, it pumps a bunch of values through. And in particular, what I did here is I changed this test not to propagate multiple ones through, but as soon as the first cycle's done, we start propagating random values on the input. And that way, at exactly this many cycles, we should have the correct value. And then before and after that, we would get incorrect values. So that means that 1, I validate the actual latency of the pipe, and 2, I make sure it's not using any stale values. Otherwise, we'd get the wrong result. So then I just test it with some actual values from the prototype with the GL front end. That's where I got these. So at least I knew it would work with those, because I also knew the Rust code worked with that. So that's perfect. And then I modified this test and it was clear that that was the issue. So then it was easy to fix. And then then I got this. So that was pretty cool. This seam bug was a little harder to track down, but again, because I had a software prototype, it was easy to kind of guess what was happening. And the idea is that when I'm doing texture filtering like this, first of all, when I'm sampling the triangle within a pixel, I want to sample the middle of the pixel. And so the way I do that is when I'm figuring out like all of the edge functions and everything, I actually offset by half a pixel before I do all those calculations, which that's how you do that. But then in addition to that, I also want to sample, when I'm sampling the texture, I want like 0, 0 to not be the center of that lower left texel. I want to do what GL does. And again, this is kind of arbitrary, but I just chose what GL does because I am familiar with that. But GL, if you want to actually sample that pixel, you actually need to do 0.5, 0.5 in texture space. So again, the idea is that would be the middle. So 0, 0, like here, should actually be like -0.5, -0.5 in texture space. So again, I bias the texture coordinates as well when I'm actually going to interpolate those. And that's kind of the easy way to do it. And then, but then what happens here is that I had those multiplies unsigned when I was, so I would take 1 over W and then do 1 over that as I was interpolating. And then I interpolate 1 over S and T, and then I would multiply those by W. But if that 1 over S was negative or 1 over T was negative, and then I didn't unsign multiply with W, I would get the wrong result. And that's why you see these crazy artifacts on the edges. Now, again, with W being 1, you only just see like a seam here. But with W actually changing over the triangle, it's much more obvious that this is something this was changing really fast because these were really like flickery, as you might imagine. So then I just had to add sign support for multiplies in my HDL, and then this was a trivial fix. So I thought that was kind of cool. I can show some of that code actually. This is my GPU. It's mostly this pipeline, and here this was the difference, right? Instead of S times W, because everything's unsigned in Kaze right now, I did mul signed. I might add, I've talked about this a couple times, I think. I might add like a next layer of abstraction on top of this in my HDL so that you would have signed signals and unsigned signals. But right now everything's just unsigned, and then you do the ops as signed when you want to interpret them that way. So maybe I'll make that change. I'm not sure. But yeah, that was it. And then there isn't that much more interesting here. Like now this approx reciprocal has a lot higher latency than I thought. I think I originally had it in like 5 cycles, but now it's like 13 cycles. It's very accurate though, and it doesn't really matter that that's that many cycles. But that's what happens there. And then in these different stages, we just do what we can. But then when I do like nearest filtering, the way I do that is I take these S and T and I just lock them. Or no, the fractional points of those weights, of the 4 texels, or like texture raw texels that you're going to read, I just clamp their blend weights to 0 or 1 for the fractional S and T. And then I think I do something similar for, maybe not. Yeah, anyway, like that's just how I do that. There's another thing too with how this memory is kind of put into different banks, which is kind of confusing. Actually, I'll use draw.io for this, which I kind of want to talk about. Which is this swap weights depending on pixel offsets. Don't do that. Create new blank. So the idea, actually, I can demonstrate it really well with these grid lines if you guys can see those. Maybe not. I'll just draw over them, then you guys can definitely see. So the idea is, let's say we have like a texel. There we go. Actually, I only wanted to draw these 4. And then I will duplicate this. There we go. So the idea is that if you're going to blend some kind of texel, you have like your sampling point that you're sampling the texel from. So let's mark as red or whatever. And this is going to be somewhere over some texels. And so typically what you do is you sample this and then the next ones around this. So you can see as this kind of moves around. No worries, Daniel. Thanks for hanging out. So as this moves around, you can see like if I were to sample this and then the next texels, it would just be this plus one, whatever. But as we move around, this plus one might change. So if I organize this texture memory to be in 4 different banks, which is what I do so I can read 4 in one cycle. In fact, I'll actually do this just to kind of show that these are the texels you're blending from and you can see how they overlap. In fact, it's always the same size here, so you can even see. You either overlap only 1 pixel or 2 or 4. Those are the only cases you have. So first of all, that's kind of important. But then again, I interleave these into different segments in memory. So like this is one, this is another one, this is another memory, and then this is another one. So again, I can read all these 1 per cycle. And again, the cool part here is you can see if I move this around, this like sampling point, it only ever overlaps each color once. And again, what that tells us is that in texture memory, since it's like interleaved like this, we can always read all the memory that we need with a single read to these 4, a single read from each of these buffers. That's basically what I'm trying to show. And that the only really complicated part is determining what the indexes into those buffers are. And then sometimes you have to swizzle them. So like here, the top left pixel is from the blue buffer, but here the top left pixel is from the green buffer. So there's some extra stuff here where I determine, like I will actually swap the weights instead of swapping the pixel data here. For these fractional values, that's actually how I swap this. I take the lower bit of the whole value, which is swaps as I go like this. And then same with T. And then so I'll swap the fractional components around if that lower bit is set. Because again, these fractional components are like 4 bits, whereas the color data is like 32 bits, right? So I have smaller muxes that way. And then what's the other thing I do here? I think it was just determining the actual buffer positions. And where did I do that? I mean, I think it's here. I think it's just... So each of these buffers is half the dimensions of the whole buffer. So I would normally shift those, but then I add a bias in some cases. So I think buffer 0 gets a bias, buffer 1 doesn't. And that's what this math is doing. So you can see sometimes these add a bias before they take these upper bits, which is the same as shifting in hardware. Whereas some of these just take the upper bits or lower bits. Anyway, I'm not doing a very good job at describing that, but that's kind of a visual representation of what that stuff has to do to make sure we always read the right texels, and that we only issue as many as 1 read per memory bank. So that's how that works. I think this is really common. I think this is like the standard way to do this, but it was kind of fun to actually implement. So that was like a complicated thing. And I don't know if that scheme will stay now. It probably will. As I implement a texture cache, I'm probably going to still maintain 4 buffers. And then I think I'll still maintain this like grouping for the texture memory. And then when it goes to fetch the texture cache, it'll actually fetch from maybe 2 different caches in this case. Or I'm actually not sure how that's going to work yet, but I need to figure that out. I'm getting already like an hour into the stream, and I don't know how much farther I'll actually go today. Just because I've got a lot to do. So I think I'll continue talking about what I've been doing, and then maybe call it quits a bit early today. Bruce Buffer, it's time. So dumb. But yeah, the sim harness for this is basically just reading and writing to these registers and then ticking the simulation as we wait for the buses to tell us that things are okay. Really simple. Whereas the model devices actually doing work, and that's why it's a lot faster. Yeah, so buffers, or I mean caches. I think I have check out read cache, which is a branch that I pushed today. I wrote this a while ago. Just gonna check this out. And remove some old stuff. Yeah, so this read cache thing, I think I add sim read cache. This is gonna build. Now I'm probably gonna drop frames. Maybe not. Okay, so a couple of funny things. So first of all, this read cache. Let's see. I kind of want to draw pictures about it. So the idea here is that this is our cache. And we have essentially read requests that come in. I think I made this diagram way too large. And then read data. I put parentheses around the read because it's also rad data. And I'll make this way smaller. No, that's not what I wanted. Let's do that. That's easier. All right, here we go. So the point is we have this, and then we have actually these same things going the other way at the bottom. All right, I'm just going to get a little sloppy with my arrows here because who cares? So the idea is that like there may be something on this side actually issuing read requests and expecting data. So this might be GPU or CPU or whatever. Also an audio unit maybe, which makes a lot of sense if you just have the audio unit, you know, streaming out, and then every once in a while it might request some new data, like whatever. So this thing at some point wants to read memory, and it needs to issue a request. And typically what you want is you have different cases. So the memory down here is what this is actually issuing to here, mem. And the reason we have a cache here in the first place is that this memory usually has a long latency. Usually has decent throughput, but a long latency. So if you issue a read request here, you might not get that read data back from the memory. Oops. I have this backwards. Something like that. The data might not come back from this memory until like 30 cycles later, which is really crappy. In the best case, you want it either within the same cycle or the cycle following. And the best we can do with the memories that I'm using in this FPGA is that we get them on the cycle following when we issue the read request. So ideally, we want that consistent 1 cycle delay, but this memory will usually have like a 30 cycle delay. And that's a cost that we pay for because we get a lot more capacity. This is like, you know, megabytes, where the cache, like internal memory on the chip, is like kilobytes range. On modern SoCs, it's a lot more than that, but not on an FPGA, especially not a low-end one like I have. So yeah, so the latency here is really high, and to hide that, what we do is we put cache memory here. And this memory is on the order of like kilobytes, but it's a lot faster. So ideally, what we want to happen is once this read request comes in, we read the memory here and then return it. And we're able to do that as long as the memory in here actually matches what's in this cache. And because this is a lot smaller, we can't always match this, right? But the idea is that sometimes we're going to read this and we're going to see if, oh, was this read in this cache? If not, we actually have to go to memory and then bring it back. Otherwise, if it is in the cache, then we return the data. So pretty basic. So the way we do that is in addition to the memory, we keep track of, actually we split up the memory into different segments. So let me kind of draw this. I didn't think I'd be explaining caches today, but why not, you know? I kind of have to describe caches in general before I get to like how a design might work. So typically what we do is we separate the cache into what are called lines. And each one of these is essentially a different memory. And usually this is a bit wider than the granularity of this, but it doesn't really matter. So in this case, one of these might be 128 bytes long. And there's usually a lot of these, as you can imagine. Many of these in between here. And so each one of these has actual memory in it. And in addition to that, we add some additional things per line as well. So this will be what we call a tag. And then there's an additional valid bit, which I will make really small. So this is roughly to scale. And each one of these is replicated. So in a given like cache line, you usually have the data, called data here, and then all these valid tags. So on system startup, we go through all these valid tags and we mark those as invalid, such that none of these actually represents data. So then what we do is once we get a read request, that read request has a big address. And we can actually split that address into different components. So if we have different parts of that address, it might look something like this. I think this is maybe more accurate here. Yeah, something like this. And let me actually look up something here, because there's some names here I just want to make sure is correct. Index, that's what this is called. So I can call this like upper bits, and I'm going to call this the index. And so typically what happens is you take this address and you split off different bits in that address. You have the index bits and then these upper bits. And so you take the index bits and you use the index bits from that request to determine which one of these lines you have that this would point to. So let's say this index were 6 and I have an 8-line cache. Then that would mean the index points to this entry. And so when a read request comes in, we need to read the data and then the tag and the valid bits for all that entry, or for that entry. And on the following cycle, we'll actually get all that back. And then we can say, okay, was a valid bit set? Yes, it was. Then, okay, we'll just return the data immediately. If it wasn't set, then on the following cycle, we need to say, okay, we need to go get that memory. So then what we do is we take this address and we ship it on this read request to the memory. And once the data comes back, we populate this data with the data that came back from the cache. In the tag, we put some of these upper bits. In fact, all of these upper bits. So we can even call this the tag part. We put this tag in here, and we also need to make sure that matches, by the way. And then we mark the valid bit as valid. And that way, the next time we get a read to like the same address or at least the range that this data covers, we can check for the given index of the read, was the valid bit set? So we actually had data, and did the tag match? Because it's totally possible, since this is so small. Like in this case, if this actually were 3 bits and you'd have 8 lines here, then every like 8 lines, I'm also illustrating what's called a direct mapped cache, which I'm not really going to talk about associativity here. But anyway, basically every 8 addresses actually would have the same index, and you want to differentiate the first like entry in memory versus the 8th. So you need to have this additional tag to make sure that those are different between different requests. So that when you have an index for 2 addresses that maps to the same line, you can actually accept or reject that, like determine if that's actually the data that's valid. But anyway, this is basically how it works. But that's a little bit complicated to implement because we don't know that for the given line that we actually have the data that we need for the request until the cycle following. So what we have to do whenever we have a request is we have to, let's do this, do back. Okay, I don't want to do that. Do back. And let me do this on top of this. Really? I can't do that? That's annoying. Okay, that works, whatever. So we actually need to, man, why can't I draw arrows how I want today? This normally works. Screw it, I'll just delete this box. Our cache is here. So we need to actually stick this into a request buffer. And then on the cycle following, we need to stick this into the request buffer, and we need to stick this into the actual cache tables. So we take this request and we send it to both of these. And the cache tables expand. That's what this is over here. Is this cache tables thing. And then on the cycle following this, that's when we know that we actually get the data that we wanted. And if that data was a match or not, so we have some match logic, which I'll actually do as a cloud. I think that's pretty typical for this kind of diagram. So then we get the data here, thing in the request buffer goes into this. We take the data from the cache tables, and if they were a match, then great, we can send the data back here. If not, we have to issue this thing from this request buffer to the read, and then make sure this can't issue any more reads, or if it can, we need to buffer those in some way. And eventually the read data comes back and we match it, and then we write back into this cache table buffer and then return the data. You guys can probably tell why I'm not like an educator, because I'm not prepared at all for this. I'm just kind of rambling, but this one cycle delay thing is kind of difficult because you don't know if like the current issue is going to be valid or it's going to hit or miss. You need to always delay that by a cycle. And you want to do things like if we have a request in this buffer, that means we issued a request on the previous cycle. In fact, I can send this to here to make sure it's clear that it's on this cycle. So if the request buffer is actually full, then we know that we had an issue last cycle. And whether or not that's a match determines whether or not we can accept a new match. And if it wasn't a match, we need to, again, issue this stuff, which actually gets issued on this cycle. And then we need to keep issuing that until the issue goes through, and then we need to go into a state in the cache where we can't accept any new requests until we get the data. And then once the data comes back, we have to do another actual write to all this stuff. And then, yeah. And this is also the simple case, right? Because this is only for a read-only cache. Whereas writes get more complicated because we might need to like keep this, we might need to do other updates to this data. So if we got like a write request, then we do the same kind of thing where we have to access the line, but then we don't know if that actually was in cache or not. If it wasn't, we still have to go back and read the data and then modify it before we put it in, or put it in and then modify it or something. There's other ways you can do that. Like you can just do like a write through cache, or you can have writes where you don't actually load the data on writes, like a cache like that. In fact, I think modern processors have these non-temporal stores, which just bypass all of this anyway. Like all kinds of different schemes on how to do this. And if you guys are really curious about that, the book I would highly recommend for that is Computer Architecture, A Quantitative Approach. I've talked about this book a lot because it's really good. And I'm not going to attempt to explain any of that stuff further, or the benefits, because that book will do a much better job than me. But yeah, the point is that a write cache is going to be even more complicated. But at the same time, it's not terrible either, because usually on a write, you don't actually have to stall the processor anymore, or whatever is requesting reads or writes. because you can just like put that in a FIFO and then process it whenever you can. If this is going to be doing like reads and writes every cycle, then you eventually will have to stall that if that write buffer gets full. And you have other things like if that write is going to affect data in the cache, you need to make sure that's updated. So there's some issues here and there, and you don't want to, for example, return data from a read if you haven't actually applied that write to the cache, and you can't necessarily apply that to the cache unless you've read it. But maybe sometimes you can pull that data out of the requests or out of the write request buffer or whatever. Like a lot of different ways that this can be done. But I just started with the simplest, which is this scheme here, this just read-only cache. So I started that a few weeks ago, and I've been working on that now. And the other thing is that I got it wrong in a couple places, which I might be able to talk about meaningfully. This is still in like dev stages. This isn't hooked up to anything yet. I just have the RTL itself, which I think is in here. Maybe it's not. Maybe it's just in this build thing for now. Yeah, that makes sense. I'm not going to talk about this big comment here now. But yeah, this is the RTL for that thing. And one of the things that my HDL lacks, which I think I need to fix soon, is a way to get like actual trace data out of this. So I think you guys have seen me on stream a couple times hack like a waveform view out of this. And the way that I've been doing that, just because it's easy, is I go to this WaveDrom site, which this is a tool that's meant for drawing waveform diagrams, and it's really good. Like you get these kind of diagrams from a simple JSON object with a particular format. So I really like this thing. And of course there is of course like these digital waveform. I don't remember what the format's called now. What's that format again? VCD, which is a value change dump. That's like the standard format, but this also basically works. So what I do is I actually generate a wavedrom object, because again, this is easy to output. And then I just kind of plug it into one of these viewers. You can see this. So this was me debugging the cache by outputting this. And the language doesn't support this, which is a mistake, right? Like the language eventually should support actually outputting proper stuff when you do a sim. But I don't have that yet. So I actually hacked this trace object here. And then I'm specifically updating stuff. I think how did I do this? I honestly don't remember how I hooked it up, but I hacked it. That's the whole point. So that I'm like explicitly doing all this state tracking and everything, and then producing this diagram, which is bad. I need to be able to leverage the fact that I have a compiler here and output this directly. And most other HDLs will actually do that. So I could alternatively, I could also just dump Verilog and then run that through a sim. But since I have my own sim anyway, I want this to support that. But I haven't implemented it yet. So here you can see, like, this is the behavior I talk about. Like here, this primary bus, this is the thing that's issuing the reads. And then this replica bus is the thing that it will forward the reads to if it needs to. And then I added some debug signals to pull out the states. This is the state of the cache. It's either invalidating itself. So these first few cycles, you can see this bus isn't ready, and that's because the cache isn't accepting any requests, and that's because it's invalidating itself on reset. And by the way, the reason I validate it on reset or spend a bunch of cycles doing that is because this is an internal memory, and on FPGA you can actually load those kind of memories with some contents as startup. So I actually don't need to do this, but I want to implement this invalidate feature because I need it for the system to behave correctly anyway. So I thought, why not leverage that and do it at startup too, which is more like what an ASIC would have to do. But I actually don't have to do that on FPGA, so I might remove that. Anyway, it spends a bunch of cycles clearing that, and then you can see it signals that it's ready. And this whole time, the test harness is trying to issue a read to address 0, it looks like. And you can see on the cycle following this read, instead of returning data, because the cache doesn't have that data in it because it's all invalid, you can see that, here, the cache after invalidating goes into this like ready state. I think it's active state. And you can see here, once it accepts that read, it wasn't in the cache. So you can see on the cycle following it, immediately it issues that read to the underlying thing. And in this test harness, just to make things simple, I only return the read on the following cycle. I might spread that out just for testing purposes, but I think I'm going to do like this big fuzz test with this thing to make sure this is correct, because I really want to be able to trust this. But you can see here it issues the read to the underlying memory, and then you can see it goes into a state where it's going to wait for that to return. On the following cycle, it gets the data back from the underlying memory, and then what it does here is on that same cycle, it looks like it sends that data back to the primary, which is great. And you can see this is the data flowing up there. It overlaps just because the way I did the diagram and I was lazy, but whatever. So yes, the data comes back and it's shipped back to the primary immediately. And then you can see the primary on the cycle following, once it gets the data, it issues another read. And in this case, the read actually should be cached, right? Because it's to the same address. You can see I also dumped some bogus addresses in between actual valid reads just to make sure those aren't used anywhere. But anyway, again, this read should be cached, and you can see on the cycle following, indeed, the cache does return data, and it's the same data, and it doesn't issue reads to the replica below. So this is what debugging something like this actually looks like. But the behavior is basically what I described in that horrendous diagram earlier. And I think I made some mistakes here initially. I don't remember exactly what they were, because I think this basically works now. I think this is more or less done. I just need to do a lot more testing on it. But how did I do this? I think this, because I have this buffer, this current issue valid. So this current issue is that like buffer that I have for the request. I might call that request buffer and request buffer populated or something. But I think I had this state not resetting properly initially, and that broke some tests. Because I also have, this is kind of a recreation of the actual test. So this is the test that we're basically running there and then getting the trace dump of. You can see here it's more described what's happening. Issue read to 0 and then deassert that. Cache miss should be observable by the fact that we can't issue. Cache propagate on the next cycle. So I'm testing the behavior here, and also inherent in this behavior is some of the cycle timing with the cache. But as you can see, it's a basic unit test anyway. I'm just like, sometimes I tick the clock and sometimes I propagate signals through the design. I feel like I'm talking so fast and just flying in this in this stream. But yeah. If this is going to be a CPU cache, I might actually make this two-way associative. I'm not sure yet though. And right now also this isn't that useful for the CPU because of the way that I have the memory hierarchy set up. It should actually help performance a little bit on the cases where it hits, but I need to do more testing before I actually hook it up. But I gotta be honest, I kind of just don't want to do that right now. I've been working very hard this week, and I'm actually really tired, despite how much energy it might seem that I have. Anyway. Yeah, I think I have a test where I just read the first thing and then make sure that that is a hit both times. I have another one where I try to read everything through it, and it stops as soon as it finishes reading the data. And then I also have one where I read everything, but I also hook up a delay such that this down here returns like 40 cycles later or something. I don't remember what that delay was. 30 cycles. And I do that just by adding a bunch of registers. That's funny. So yeah, I guess my point is I need to, at some point, implement this kind of trace stuff automatically so you can generate code to do this. And I probably wouldn't write it as this wave drum thing. I'd probably do a value change dump. Maybe I'll support both. I don't know. But I've just been lazy about doing that because I actually haven't had to do this very often, this kind of debugging here with the system. Because most of the time when I'm writing these kind of tests, these like really test bench kind of things, I don't really feel like I'm that blind actually, because I can see what all these signals are over time. But sometimes it really helps to see these together, especially when I had to debug this, because I think I had, again, this issue thing. Where is it? I think it's up here. This has current issue wasn't wasn't transitioning properly, and I don't remember the logic I had before that was broken, but it wasn't this. And what ended up happening is that this would work, but then it would think that it still had an issue on the cycle following this, where it actually wasn't issuing any more reads, and so it just kept returning data that was cache data, but yeah, it returned a lot more data. So again, that was easy to catch because my test also has this part right at the end where it says cache should not return more data on the following cycle since no read was issued, right? So we'll do that. But I think like with the FIFO here, I also have this test where I do a couple things. So there's this librs where I do these like unit tests. So say like the FIFO is empty on reset and it's not full on reset and things like that. So very basic tests. These are really useful. But also I want to like really stress test this. So I also add this program in main where I can give it a seed and a number of elements. And what it's going to do is it's going to essentially pipe that many elements through. So it'll write that many elements on one side and then read that many elements on the other side. And it makes sure that we always get all of the right data as it's doing that. But you can see here that whether or not it reads every cycle is random, and whether or not it writes every cycle is random as well. So that kind of adds this element of like timing variance. So if you put a bunch of elements through this, it should still work. And that's how I tested that. And I would really like to do that with the cache as well. But again, I think I might not actually, because I'm really tired. So I think I might actually go. But yeah, I feel like this stream was important to get kind of caught up with the project and talk about where it's going to go. And I need to work again a bit more on some of the documentation for the project, because I think I added some things here, like the description of the bus signals, which I also want to, in fact, that's easier to view in GitHub because it's markdown. But in this doc directory, I added this bus.md, and this here, it just talks about what the signals are on the buses. And I actually want to take that wavedrom tool and generate some of these diagrams for those buses as well, which I think would be really useful to have. And in addition to that, I also have, let's see. Yeah, like this topology diagram for the system. And of course, this is going to change. And I also kind of want to do this to draw out the pipeline stages of the CPU, which I think will also help me visualize how we're going to do the stalls and everything, which we're going to need to eventually do. But again, we can't properly pipeline the CPU unless we can keep everything fed every cycle. And we can't do that without caches. So we're working on caches. But yeah, I think I will work on that later. By the way, Dark Second, thanks again for the sub. I really appreciate it. So yeah, the caches are going to end up being here. The CPU is going to have caches internally. So it's still going to be one bus in and out of the CPU, but it's going to be mux between those caches. So the CPU stages will talk to different caches respectively. Standard stuff. And then yeah, this color thrust actually is here now. So that needs to be colored in. But then the color thrust as well is actually going to be a primary on this mem bus, as are some of these other things. So this diagram is going to get more complicated, but it won't be too bad, I think. In fact, I might even remove the 128-bit data path from the color thrust, or from this bus entirely, and just make that a 32-bit data path, so you'd use those two read and write registers, and then only hook up the 128-bit data path to this DMA and give this its own DMA. It's going to be more complicated, but it's going to work. Anyway, yeah, I think I'm going to go because I'm tired. But yeah, thanks guys for hanging out, and I will see you next time.